OK, so that was coarse-grained multithreading. We're going to move on to figuring out how to mix instructions of different threads in the pipeline at the same time, and mix them in the same, and issue two different threads instructions at the same time to different pipelines. So the idea here, this is called simultaneous multithreading. And actually, let me start off with a picture of what this looks like. Let's work backwards in the slide deck here for a second. So we have a 4-issue processor. And this is our issue width. And this is time increasing going down. Each of the different patterns represents a different thread. And the idea here in simultaneous multithreading is that you can execute instructions from different threads into different pipelines simultaneously. Now, this gets quite a bit harder than this basic design here, because now we actually have to read from the register file for different threads simultaneously, and we have to fetch different code from different program counters simultaneously in this processor. So simultaneous multithreading, where it came out of was people were building complex out-of-order superscalars. And these complex out-of-order superscalars had all this logic to be able to track different dependencies between different instructions and to basically restart sub-portions of instruction sequences. So this is like you take a branch mispredict, you had to kill all of the instructions that were dependent on that branch mispredict and leave other ones that were not there alone. And when you have this out-of-order mechanism, you have all this extra logic there to figure that out. Dean Tolson, Susan Eggers, Jim Levy came up with this idea that, well, what if we try to utilize all the dead slots in our out-of-order superscalar, but intermix different threads in there simultaneously to fill the time? So they did this study back from ISCA in '95, and we ran a bunch of different applications. And this rightmost bar here is our composite or our average here. And what you should figure out from this is this black bar on the bottom here is how long the processor is busy, actually doing work. And the rest of this is different reasons the processor was stalled. So we were stalled on instruction cache misses, branch mispredictions, load delays, just pipeline interlocking, memory conflicts, other sorts of things. And we were only using this processor less than 20% of the time. So to show this a different way, we have our multi-issue processor, and we have time here. We have all these purple boxes, which are just dead time. And we might be able to use subsets. This is very good. We actually issued 4 instructions in this cycle. But here we only issued 2. Here we issued 1. Here we issued 2 to these 2 pipelines in the middle. Maybe these are the 2 ALU pipes, and there's like a load pipe here and a branch pipe there, or something like that. This is kind of a disaster from an IPC perspective. Can we try to reuse that hardware? And we talked about our coarse-grained multithreading, which was effectively temporally slicing up the cycles here. So you run one thread, switch to a different thread, run a different thread, and you can temporally switch between the threads. But what would happen in another approach, and this was actually done in the failed Sun Millennium processor, what was going to be UltraSpark 5, they had this idea that they actually had a clustered VLIW, or a clustered superscalar, and they had a mode you could flip a bit, and you could basically cut the 2 clusters separately and run them as 2 separate processors or 2 separate threads. So you can actually decrease. Let's say you had this with 4 processor, and instead you split it in half, and you have 2 functional units running one thread, 2 functional units running another thread. Well, this has some good effects. You don't actually have to have really high IPC, or really high instructions per clock. You don't ever have to reach 4 in this design because we've narrowed the 2 pipeline widths. And you could think about trying to put them together. This is what the Millennium processor, the UltraSpark 5, tried to do, is you could actually switch between this mode and this mode. But you still have a lot of open slots here that you can't go use. So it still leaves some vertical waste. Another downside to this was you can't have one thread using all of the resources very easily here in this mode. You can't have, let's say, thread 1 use this functional unit over here in this very static design. So this brings us to full simultaneous multithreading, or SMT. And in SMT, we were able to mix and match all these different instructions. But this is going to change our processor pipeline quite a bit. OK, so let's look at what this does to our processor pipeline. Well, all of a sudden, we need to be fetching multiple instructions at a time. That's definitely a harder thing to do here from different threads. Conveniently, we can actually use our instruction queue, or our reservation stations, if you will, to go find different instructions to go execute at the issue stage of our out-of-order processor. So what we can do is we can tag the different threads independently and have that be part of the instruction issue logic, such that you can't issue, or you know that thread 1, register 1 is different than thread 2, register 1. And then you use the same logic that we've had in our out-of-order superscalars in our issue queue, or to go find different instructions from multiple threads to go stick down the pipe, or the respective multiple pipes. And conveniently, we have most of this logic already. And what's also nice about this is if you're only running one thread at a time, when you go to look in your instruction queue or your issue window, only that one thread will show up. So you can know that you don't need to go look around to other threads, and you can use the full machine. And this allows you to use the same machine such that if you have lots of parallelism, you can run different threads and fill all the different slots. And then if you don't have the parallelism and you want to exploit instruction level parallelism, you can use the slots in a different allocation and just have the dead slots, the purple slots. And you can see here we are issuing 3 instructions from the checkered board blue, and here we're issuing 4. Well, let's say it's the exact same program executing on the same cycle. You could actually have the machine such that you'll issue different amounts of parallelism, of instruction level parallelism from a thread, depending on if there's multiple threads running. And this is what these truly multi-threading machines, simultaneous multi-threading machines, attempt to do. See, there's one other point I wanted to make here. You have to worry when you're doing this simultaneous multi-threading here about priorities between threads. Because you want to make sure that you have some sort of equal progress guarantee, or some, and round robin's probably not good enough. So you need to somehow figure out how to not have one thread hog the machine and have some fairness between the different threads. So I wanted to show a few examples here. So here we have on the top, we have the Power 4, IBM Power 4 processor pipeline. And this was a non-multi-threaded machine. And the Power 5 architecture actually looks very similar to the Power 4 architecture, except they added a second hardware thread. So what they had to do here is they actually had to add more fetch bandwidth. And then they added this notion of group formation. And this group formation was the picking out of the two threads. So they could figure out what they could actually execute simultaneously at the same time. And they effectively had extra pipe stages out in front to go do that. And at the end here, you have to commit two different program counters at the same time. You can see there's definitely some complexity in building this, that all of a sudden you have to be able to basically, in your reorder buffer, kill a subthread, what it branch mispredicts, but not the rest of it. And we already have talked about how to do that in a superscalar where you can kill a subsection of the instructions and not have to kill the whole instruction sequence. Here's a different view of the Power 4 and a physical chip view here. And one of the interesting things to see is that they went with 2 threads because if they went to 4 threads, they figured out that they would actually be using the resources too much and be bottlenecking in different locations in the pipe. It was basically, they didn't have enough resources sort of over here to have it be filled. It would be filled if you had more than 2 threads executing on this anyway. So there was no sort of diminishing returns past that point. We're almost done, but I think we're out of time. Let's actually, before we do that, let me skip forward here and just summarize with all the different types of multithreading. You have your superscalar processor. You have your very, very fine-grained multithreading where you're doing it on each cycle. You have this coarser grain where you sort of do it every few cycles. You can think about cutting the processor in half and using some of the function units for one thread and some of it for another thread. And then we have our full simultaneous multithreading. So we'll pick up on this next time and finish up about some of the implementations of the Pentium 4 and how they did multithreading. But we'll stop here for today.